This video is going to look at piecewise functions. We want to be able to evaluate a piecewise function at a given value, graph a piecewise function, and to determine if a piecewise function has points of discontinuity. So first of all, just a general concept of a piecewise function is just a function whose domain is divided into several parts and different function rules are applied to each part. So it's basically just taking a couple of different functions and putting them together. So this function says f of x equals 4, which would be a constant horizontal line, if x is less than or equal to 0. So where x is less than or equal to 0, which would be this left side of the x-axis, is going to just be the horizontal line at 4. Since we're going to go up to where x is less than or equal to 0, we're going to put that closed dot on the 4. The second part of this function says when x is greater than 0, then we're going to use the line 3x minus 2. So that line would have a y-intercept of -2 and a slope of 3, and the line would look something like this. Here, this point should just be an open circle because of the just greater than 0 part here. So that's just kind of what a graph of a piecewise function would look like. Here's another piecewise function. It has 3 parts. So here we're just looking at evaluating some of the piecewise functions. So we want to evaluate f of -10. So what we need to do is look at this value here and decide which of these regions that it goes into. So -10 goes into this region because -10 is less than -4. So we're going to use that first region. And so we're going to just say -10 plus 4. Which would give us -6. We can also look at it on the graph here. When we go to x equals -10, my y value is -6. Next, we're going to evaluate f of -4. So we have to go find where -4 is included in the region. So if we look at -4 here, we're going to have to use this second one because that's where x is or equal to -4. So we're going to use the second function there. So we're going to go 2 times -4 plus 5, so that's going to give us -8 plus 5, which is -3. So again, if we want to look at our graph here, if we want to look at the graph here, this would be -2, -4, and so I'm using this point right here. Next, we're going to evaluate f of 0. So 0 is between -4 and 1. So again, I'm using this middle function, so we're going to do 2 times 0 plus 5, which will give us 5. So here we are at 0, and that's giving us a value of 2, 4, 5. Next, we're going to evaluate f of 1. So again, that is included in this region that we have outlined in purple here. So again, we're going to use this 2 times 1 plus 5, which gives us 7. So here at 1, we are getting the value of 7, which is this point right here. Finally, we have f of 5. 5 is greater than 1. So we're going to use this region right here. So we're going to do -5 plus 3, which will give us -2. So at 5, 2, 4, 5, we're going to get -2. So this point here. So really, when you're evaluating a piecewise function, just look at the value that's in the parentheses, determine which range of values that goes with, and then use the corresponding expression to do your evaluating. Continuing with this same function, we just want to look at a couple properties of this function. So what's the domain of the function? Well, the domain is all numbers less than -4, and between -4 and 1, including -4 and 1, and then all numbers greater than 1. So really my domain here ends up being all numbers, so we're going to say -infinity to +infinity. What is the range? To get the range, we want to look at the graph. So taking a look at the graph, these two lines are going down forever, so my domain goes down forever, and then we come up, and then the highest point that we hit is right here. So this is going to be 2, 4, 6, 7. So my domain goes down forever, and then we hit all of the y values up to and including 7. So my range is going to be -infinity to +7. Include the +7 because we have the closed circle there. List any points of discontinuity. So remember here, we're going to start tracing this function from the left. I'm tracing the function, and at this point I have to pick up my pencil to jump down to here, and that happens at, this is -4. So we have a point of discontinuity at x equal -4, and that point of discontinuity is non-removable because we can't just shade in this one point here and have it be continuous. We would have to draw a whole line segment in there. Again, if we continue tracing this function, we're going to get to here, at which point we have to pick up our pencil again. This is happening at 1, so we have another point of discontinuity at x equal 1. And again, that point of discontinuity is non-removable because we cannot just shade in one point and make it continuous. Finally, we're talking about increasing, decreasing, and constant regions here. So again, I'm going to start from the left and start tracing this graph. As I trace this graph, I am increasing until I get to this point where we have to pick up our pencils. We're going to say we're increasing from negative infinity to negative 4, parenthesis on the 4, because on this section of this graph, there's an open circle there. Once I pick up my pencil and I start tracing the next section, I'm still increasing. So we're going to continue the increasing region here from negative 4 to 1. Square brackets on both of those because on that section there we had closed-in circles. After that, once I start tracing again, now I am going down, so we're decreasing. So we're decreasing from 1 to infinity. Remember, when you're giving increasing and decreasing regions, you're always working from left to right, and you're giving those regions in terms of the x coordinates. Here we just have an example of a piecewise function that is the US tax brackets. We want to be able to graph the piecewise functions on your graphing calculator. So if you take a look at your calculator, we're going to go to your y equals, and we can put this piecewise function into the calculator. First, in parentheses, you're going to put the first expression in. So I'm going to do the x squared plus 2. Close that parenthesis, open a new parenthesis, and then you're going to put that domain restriction in. So you're going to type x, and then we have to do less than or equal to. In order to get that, you're going to go second math and choose the less than or equal to sign, which is number 6, and then type in the 1. Close the parentheses on that. Then you're going to do a plus sign, and you're going to add that second expression. So here we just have x, so I'm just going to put x in parentheses, and then open a new parentheses to do the rest of the domain restriction. So x again. We're going to go second math to get that inequality is greater than 1. Close that parenthesis. And then we can take a look at the graph, and you can see the parabola and then the rest of the line. What the graphing calculator does not show you is where the open and closed circles go, so you kind of have to know that on your own. When you come back here, the parabola has the or equal to on it, so the closed circle would be here, and then the open circle would be here. On the second example, when you're graphing a piecewise function which has more than 2 expressions to it, you have to be a little bit careful with those compound inequalities. So this compound inequality here is a little bit tricky on the graphing calculator. So let's take a look at how to put that in. So we're going to go parenthesis, and we're going to do the x plus 4. Then that domain restriction, which is x is less than negative 4 plus, and then we're going to put the second expression in. So I've got the 2x plus 5. Close the parenthesis, and then here is where we have to be careful. The calculator does not understand the compound inequality, so you have to break this up into its separate pieces. So we're going to do negative 4 is less than or equal to x. Close the parenthesis, open a new parenthesis, and then we have to do the second part of that inequality, which is x is less than or equal to 1. Then a plus sign again, and then we can do the last line. So in parentheses, we're going to do negative x plus 3, and then in a new parenthesis, we're going to do x is greater than 1. Then you can see your graph. Again, we want to think about the open and closed circles here. So this middle line here is the one that has the closed circles on it. So we would have a closed circle on both ends of this line here, and then open circles on the other two. Lastly, we want to look at how to graph a piecewise function in Desmos. So if you don't have your calculator and you're using the Desmos graphing calculator, I want to show you how you would graph those in there. Okay, so in Desmos, you're just going to start with f of x. You can use y here too, but this will allow you to do some evaluating later if you need to. Start with the curly brace, and then in Desmos, you put the domain restriction in first. So we're going to do x is less than or equal to 1. On Desmos, if you just type on your keyboard the less than sign and then hit the or equal to sign, it will change it to that less than or equal to sign. Then you're going to do the colon and then type the expression, which was, in our case, x squared plus 1. Then type a comma, and then you can do your second expression. Remember domain restriction first, so we're going to do x is greater than 1, colon, and then we just need x. And that is my piecewise function there. We're going to do the second one right on here as well. So here I'm going to do g of x equals curly brace. So this one was x is less than -4, colon, and then my expression was x plus 4. My second domain restriction is -4 is less than or equal to x, which is less than or equal to 1. Put the colon in there, and then we need our second function, which was 2x plus 5. Do a comma, and then finally our last one, which will be x is greater than 1 for our domain restriction, and then our function was -x plus 3. So the nice thing in Desmos is that it does understand the compound inequality as your domain restriction. Again, just like with your calculator, Desmos does not give you the open and closed circles.